Hello everyone. Today we're going to discuss about e-value and it's a pleasure to be here. S- So my name is Lucas Mena. I am an orthopedic surgery resident here in Brazil and I am part of PPCR since 2019 and this year I'm applying to be a senior TA. As disclaimer, I don't have any conflict of interest for this presentation. All right. So to start the discussion, I think it's important to us to remember what a confounding is, and there are several definitions for confounding. And one that I particularly like is using graphs. So to a factor to be considered a confounder, it needs to be an ancestor to A and to B. So here in this case, we can see that C, the arrow points towards A, and C, the arrow points towards B. It's important to highlight here as well that this usually you would not represent this arrow between A and B, but for pedagogical reason, I decided to keep on the slide. All right, so we already remember using a DAG what a confounder is. So considering that you have a study and how can you address it? There are several ways. Most of them occur during the design phase of the study. So one of them that we are already well aware of is randomization. The idea of randomization is that you assign the exposure. Therefore, it's not possible at baseline to a factor to be an ancestor to the exposure because the exposure itself was randomized. Um, this is useful in RCTs, but usually in observational trials, you don't see that because randomization is not possible. But there are other options that can be used on observational trials in the design phase. One of them is restriction. So you can select a particular group that you want to study, and when you are establishing your inclusion and exclusion criteria, you are not just only establishing the your target population, but you can also use that in order to restrict for a confounding factor. So, for instance, if you think that diabetes is it could be a confounding factor in your study, you can restrict your population for this factor. A second way, mostly is on case control studies to address confounding on the design phase, is matching. Matching is well suited when you are using a complex nominal variable. And what is that? There is a variable that you it's hard to you to divide people by this particular variable. For instance, neighborhood is a good example for a complex nominal variable because there are plenty of neighborhoods, and if you try to to use on the second phase during the analysis, a neighborhood as a factor, it might not be possible with your sample size. So you might consider doing matching in the design phase. There are other ways to address confounding. There are ways where you're doing the data analysis, so stratification is one example, and other types of regressions. But in this particular lecture, we are gonna focus on unmeasured confounders. So, what actually is a unmeasured confounder? So you can have so sometimes you know that a factor might be causing A and B, but you didn't measure on your trial, or you're not able to measure in your trial, or even it's too expensive to measure in your trial. But you still know that um, that that this might be there, and in some cases you know that there are unknown confounders, but you can't establish what the unknown confounder actually is. But you believe there is a third factor playing on that relationship. So what you do when you have a measured confounder? Uh, there are plenty of options. Some of them requires a lot of extrapolation about the data and needs a lot of assumptions. One of them that is actually way straightforward is calculating the e-value. So its value, it's a way to calculate the minimum strength of the association between the risk ratio and the unmeasured confounder that would need that you would be able to cancel the association that you saw between treatment and outcome, between or exposure and outcome. So to calculate e-value, in order to calculate e-value, uh, for there are several formulas, uh, but most of them are very straightforward. And here is one example for risk ratio. So it doesn't require much, and it doesn't take assumptions about. It doesn't take much. It doesn't take many assumptions. To us, I brought today a paper to discuss. In this paper, the authors tried to evaluate injuries in participants of indoor bouldering. And when you see the results, there is a funny statement that participants who use heavily downturn climbing shoes had a higher risk of having an injury. So for those who are not familiar with climbing shoes, those are the most common models. And when you start climbing, you would probably start with a neutral, and when you develop more your skills, the routes that you start doing require a more aggressive design. So so when you read that the shoes are associated with more injuries, uh, this 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 is a red flag that you need to be aware of, because you think the climbing level that the participant do. So I'm a really good climb. I'm a good climber, and I buy uh, aggressive shoes, and then because I have aggressive shoes, uh, and so I'm really good climber, and I buy aggressive shoes, and I'm a really good climber, so I am bolder enough to go to more difficult routes where I can get injured more easily. So in the case of the study, they did not adjust for climbing level. And one reason why is that it's really hard to calculate. It's really hard to measure climbing level, because there are plenty of scales used for measuring the level. From there's the France one, there's the Yosemite one. There are several. And between the communities, people, depending on where they are, they're gonna use one or another. So it's quite hard to measure that. And then but then they made this statement about the shoes. And if you decide to calculate the e-value, there's the website. You just put e-value calculator, and it's from the authors of the original paper. And you can see that the e-value is not that big. It's This value is 2.5, so it's almost the same as your point estimate. So if you have something that is 2.5 times the risk factor, you might have a null finding. It means that a really not that big confounding factor would be able to eliminate this relationship that they figured out. Um, that that's just one example. The biggest lesson about the takeaway message of this lecture is that confounding it's a good way to measure uh, the strength of your finding. If only if only a big confounder would be able to neutralize your effect, so you might be safe on driving your conclusion. But in some cases, like in the case of the climbing shoes, you see that small things could be creating this relationship that is not true. So thank you for listening, and it was my pleasure to present this lecture. Goodbye, everyone.